Hello everyone and welcome back to OpenGL, and God, it has been a fat minute since I've done anything on this channel. Really, I will be doing some sort of stream at some point, and then within the next week, and I'll explain some more. But anyway, I just wanted to post somewhat of a short video with some code I recently wrote where we actually deal with primitive collision reactions. So this will be kind of a stepping stone, just setting up kind of the framework, and then we will be able to add more customizations to this to get more realistic collisions that are not just completely elastic. So when we think about collisions, one thing that you may think of is the normal force. So that's just the force that a surface will exert on any object that kind of counteracts gravity. So it's kind of the force that keeps an object from going straight through it. This is, of course, only with solids. The interesting thing here is that the normal force is always perpendicular to the surface. So you see here on this triangle, we have a normal force, and it's perpendicular to the triangle's surface. And this force is exerted on the block, and the block will not then just fall straight through the triangle because of the normal force. So when we go to handle collisions, and let's say that this block came flying in from some angle, and we wanted to see where would the block go. Let's assume for our purposes that this is a completely elastic collision. So if the block, let me see if this works. Yeah, so if the block came in from like over in this area and it struck the triangle right here, if we're assuming a completely flat surface and ideal conditions and all that, this would be kind of like a particle collision or light reflection per se, where the angle that we hit the surface with will be the same angle that we leave the surface with. So the angle of incidence is equal to the angle of reflection. So we're going to be using reflection here across the normal. So that's going to be what we're going to be looking at today. We're just essentially going to be taking a velocity vector and just reflecting it across a normal vector, which we will get through various ways. So we'll start in rigidbody.h right now, and we're going to go into the rigidbody class, and we're going to add a new method at the bottom. This is for collisions, and this one's going to be void handle collision, pass in a rigid body pointer instance and a GLM vec3 normal. So these are the only two things that we're going to need to handle most collisions, actually. Just because the instance is the instance that we're colliding with. So once again, this provides a framework for future customizations where we can store custom material data with a model, and the instance would point to that and be like, okay, if something collides here, or if this instance collides with this, we want to just delete it. So let's say the instance was a bullet, then we would say, all right, go fuck over the instance. Just say destroy, kill the instance, activate the kill switch or whatever. So we could figure that out. We'll look at something like that in a bit, probably in a stream at some point. And the normal vector is just the normal vector of the instance that it's colliding with. Okay, so that is the signature, and let's now copy the signature over to rigidbody.cpp at the very bottom, like this, like this. All right, now for rigidbody.cpp, the only thing we're going to do right now is we are going to, as I said, we're going to reflect a velocity vector across a normal vector. So we are going to say this dot velocity is equal to, oh, I need to add the rigid body tag here. So this dot velocity is equal to, now there's a reflection function, GLM reflect, we're going to reflect a vector so that the vector I is the incidence vector, so that's going to be our velocity vector. So this dot velocity, and then the normal vector n will be the normalized version of the normal. So GLM normalize norm. So once again, we're taking the velocity vector, which is the incidence vector, and we are just reflecting it across GLM normalize. And that's pretty much it for handle collision right now. Now we get to figure out, all right, where are we going to get this normal vector? Because in the end, we're going to be calling handle collision in the octree method, in the check collision self. When we say case 1, we're going to be calling object dot handle collision, or object dot, what is it? We're going to be saying, oh, object dot instance dot handle collision with the instance, which is br dot instance, and some normal vector, which we don't know what it is yet. So we need to figure out what this normal is going to be. And I'm just going to do this now. We're going to have a placeholder up top for the normal vector. So GLM vec3 norm. So we're going to be trying to populate this vector here. So we'll pass in norm to handle collision here, and we're going to be redoing, or we're going to be going back over this once we figure out what to look at. All right, so as of now, we have 4 different cases here. This one should be 4 there. The first one calls for the collision. We want to collide a face with a face. That's case 1. So what we're going to be looking at here is what's the normal vector of the face that we're colliding with. Now, if you remember, if we go into our face structure, we have a normal vector that we store. We store a normal vector here, which is cool. So what we can do with this is just if we detect a collision, we can return this normal vector, the normal vector associated with the face that we're colliding with. So in octree, we would find, all right, the object.collisionMesh.faces at j. This would be the normal vector that we return and pass into handle collision. However, it's not that simple because collides with face returns a Boolean value. So what we're going to have to do is we're going to have to go into the collision mesh function, or the collision mesh header file, and we're going to have to add some parameters here. So in both collides with face and collides with sphere, we're going to be passing in GLM vec3 ampersand ret norm. So we're going to be passing in a reference to a normal vector that we can assign values to, and the same thing for collides with sphere. So GLM vec3 reference ret norm. All right, let's head into collisionmesh.cpp, and we need to add these parameters now. GLM vec3 reference ret norm and collides with face. All right, so these methods, like I said, or the way that we're going to assign here, are going to be somewhat self-explanatory. So the first one, for collides with face, we're just going to be returning the normal vector of the face that we are colliding with. So we're going to say ret norm is equal to face.norm. So face is going to be the object's face. So the object that we're testing a collision with. So it's going to be that face. However, we can't just have this because, once again, the face normal is just a generalized one. Since we don't want to have how many ever faces for all these instances, rather we just want to have one vector and then transform it every time. So we're going to say ret norm is equal to face RB dot normal model times face dot norm. So we're multiplying the normal model, which I talked about last time or a few videos ago about why we're using a normal model instead of the model matrix, and we're multiplying the normal vector by this here. All right. This is very similar to how we calculate this norm, except now we're returning the value. All right, so that's for collides with face, and then for collides with sphere, let's go ahead and add the parameter again. glmvec3 reference ret norm. For collides with sphere, it's a little different. Because if you remember, the collision of a sphere and a plane is going to be a circle. So when we get a circle, we're going to get a center of the circle. And it should make sense that the normal vector of this will just be the vector from the center of the circle to the center, the center of the sphere to the center of the circle. We have the center of the sphere, the plane, the circle of collision is in orange, and the vector from A to B is the normal vector, in essence. So what we're going to say is ret norm, when we find if the absolute value of the distance is less than BR radius, we're going to say ret norm is equal to circle center minus BR dot center. You can kind of also see it in this image here, but it's a little less, yeah, so the normal vector is pointing outwards, and think about it, if you had a sphere, a ball, and you just dropped a plane onto it, not the vehicle, a plane, just a plane of anything onto it, it would bounce opposite of it would bounce pretty much on the normal of the plane. So what am I doing? We can just call this the unit n. What am I doing? Alright, yeah, return normal is just the unit normal of the plane. I just realized that. Alright, revelation time. But yeah, so if you wanted to use you simply just say the unit normal is the return normal. Just like that. Alright, perfect. So now that we have our normal vectors. Pretty cool. Now let's go into octree.cpp. So we have our normal vector placeholder, and now every time we go ahead and call collides with face, collides with sphere, we can simply just pass in norm as the last parameter, and it will automatically assign to the normal vector these values here. So it would become unit normal or face rb.normal model times face.norm. So we're going to get the normal vector of the collision here, and then we can pass that into object.instance.handle collision with a br.instance with a normal vector norm, just like that. So it has to be the same name here and here. All right, so let's do this for case 2. Once again, we can pass in the same normal vector, and then after we print out, we can simply call object.instance.handle collision with br.instance and norm. Now for case 3, with the faces, we're simply going to do the same thing. Norm. Yes, we pass in a norm to collides with sphere, so we can assign to it. And then after we print out, we can call object.instance.handle collision with br.instance across the normal vector normal. And then for case 4, it's going to be a little different because the normal vector is going to be equal to, so if we're colliding two spheres, the normal vector is simply just the difference between the centers. So we just have an object.center minus a br.center. Just like that. So the normal vector is just the difference between the centers. And then we call the same thing. So object.instance is equal to, or object.instance.handle collision with br.instance across the normal vector normal. Just like that. Okay. So that should be good. So let's test this out. Run it. Yep. Fuck. Ah, yes, in main.cpp, we just have to remove our tests of the collision detection because we don't need that anymore. So now let's run it. And alright. So we have our thing. We have our balls. That's a funny one. And look at that. Perfect. So I throw the ball and it bounces off the normal. Now you're gonna see that's gonna fuck it up a bit. You can already tell that's not working out well. It's not perfect, but there's a good fix that we have for some of this stuff. Let's see if I can hit the thing. Nah. So yeah, it's working pretty good. It's working as we expect. So let's play around and let's get a bigger lamp here. Let's get the size as 10.0 in the X direction, 1.0 in the Y direction, and 10.0 in the Z direction. So let's run this, see what it looks like. Alright, good. That's pretty big. That's a fat fucking lamp. So just like that. Good stuff. However, let's try this now. Let's get a little bit of a roll. That wasn't supposed to happen. But there's a bit of a reason there. Yep, good stuff. Let's try hitting it off of two things. Alright, looks good. Alright, nice. So yeah, works for the most part. However, there is a discrepancy that we had for a few of those things here. We were specifically when we collided with like the corner of the box, it was like hitting it twice, and it was like phasing into the lamp, and we don't really want that. And the reason why that was happening is because we don't have it's registering each collision or each intersection as a collision. So let's look at this again. Alright, so it stopped there, but let me turn off the reflection of the velocity. So we're just assuming that there's no resolution here. And if I do this, it registers a collision for 4 frames. Now, let's say that our collision was kind of registered late, so like the object was like already inside of a box, and when it reflected it backwards, it found it outside the box again. So it would be reflected twice, which, if you know, a double reflection just gives the same thing. It will just give you, if you multiply or if you reflect a vector once, it reflects it well, and then if you reflect that reflected vector, you get the original vector back. So we have to kind of have a threshold defined here. So we're going to go into rigidBody.h, and we're going to go to the top, and we're going to have a define variable here. And it's going to be called #define collision threshold 0.05f, and this is in seconds. So with each instance, we are now going to store the data of previous collisions, or of the last collision. So we're going to have 2 new attributes, data of previous collision, So float last collision, this is just going to be a timer, and then standard string last collision ID. So the purpose here is we may want to have a difference in time between last collisions, but only if it's within the same instance. If we collide with two instances, then yeah, let's let that happen. But if they're different instances, I just said that. If they're different instances, we want to let that happen. So we want to store both the time since the last collision along with the ID of the last instance that we collided with. Alright, so we have these two things. And now let's head into rigidbody.cpp and we'll start in the constructor. So in the constructor, we simply just want to initialize these two values. So we're going to say last collision is set to collision threshold, and then last collision ID is just an empty string. So I'm setting the collision threshold. So the collision threshold 0.05 means we want 0.05 seconds between consecutive collisions with the same instance. So I just want to set that as a collision threshold at first, or in the beginning, in case we have a collision in the first frame, and I don't want to compare a string. And this counter, the last collision, will be updated every frame. So when we call update, we also just want to say collision, or last collision plus equals dt. So we're just adding the time step of each frame to the last collision counter, which makes sense. We're just counting the time since the last collision. And then in handle collision, we're going to do something here. We're going to have an if statement. So if last collision is greater than or equal to collision threshold, or last collision ID does not equal instance.instance ID. So two conditions here, or two possible ways to register a collision, or register the reflection here. If the last collision has been more than the collision threshold, in this case 0.05 seconds, or the last collision ID is not equal to the current instance that we're colliding with. So it's either a different instance, or it's been a sufficient amount of time, or a sufficient amount of time has passed since the last collision. So in this case, we're going to reflect the velocity, and we're going to reset the counter. Last collision is equal to 0.0 float. So reset the counter. So yeah, we registered the collision, which is elastic since we're just reflecting, so we're maintaining all the energy. And then outside of the if statement, we're going to say last collision ID is equal to instance.instance ID. So either way, we just want to set the ID of the last collision to the instance ID, whether or not we've actually registered it. All right, so let's run this. And I don't think we'll see much of a difference. On slower computers, you might. Like when I was testing this on my laptop, I was. But here, since I have a faster GPU, it might not show up. But this is cool stuff. See it down there? And let's try something out here. Let's try colliding the spheres. Okay. Oh no. Vector subscript. Okay, yeah, that's an error. Nothing to do with the code that we wrote, but I will figure that out. Where'd the spheres go? Oh, okay, that's not good. There's so much energy. Let me decrease the energy that we give it. So main.cpp, we will give it 25 joules of energy. Damn. Alright, yeah, there's still errors with the awk tree that I have to figure out, but let's play with this for a bit. That's more like it, yeah. Let's try getting a rolling thing. Cool stuff. Very nice. So yeah, on slower, or what I was noticing on when I was testing this code on my laptop, what was happening was that when I would like roll it kind of horizontally, it would just fall through the bigger cube here, or the bigger plane here, just because it was registering the same collision twice. As I said, because it may register it late, so it was just reflecting it twice, so it was just allowing it to fall straight through, which is not what we want. It's cool stuff. So once again, perfectly elastic collisions. Yeah, alright. Awk tree errors, but that is okay for now. Alright, yeah, that's pretty much our basic collision resolutions. I will be posting a more complex continuation of this where we experiment with some of the other stuff that we can do. At some point, I'll be looking at like material properties, stuff like that. But I may stream something else before that, just so I can talk a bit about what's been happening. Just because I've been fucking almost radio silent. I've still been trying to respond to emails and YouTube comments, but I've been trying my best there. I think I've gotten most of them. But yeah, I hope you guys enjoyed this. We will continue this, definitely. 100%. 115% actually. But yeah, hope you guys enjoyed, hope you learned something, and I will see you guys next time. Take care of yourselves.